I want to welcome you to another statistical topic. Of course, today we're starting chapter 9. But before I go into new topic, I am actually going to release today exam 2 guide, and I'm going to tell you. Of course, there's going to be 30 multiple choice, okay, 30, and of course, that would revolve around what we did in chapter 4, 5, and 6. Now, I need you to be around on Monday and Wednesday because I'm actually um, going to walk you through some practice questions. But let me first tell you this. Of course, in chapter 5, let me start with 5. We did discrete probability distributions. Okay, every probability distribution will be tested. The knowledge, like we did under discrete probability, we did 8 distributions under discrete probability. And under continuous, we did 7 probability distributions. 8 plus 7, that would be 15 distributions. It means 15 of the questions will actually revolve around 15 distributions. Like I said, I'm going to release today an exam 2 guide. Okay? So, and chapter 4, of course, we did mathematical expectation, conditional mean or conditional mean, conditional variance, unconditional variance, conditional functions, and the like, covariance, correlation. Of course, 15 questions from that too, so making 30. So, like I said, I will release exam 2 guide today. And because I got 30 questions, and this exam is going to be held online over Zoom. We're not going to have, there's no location for this exam. The location is depending on where you're going to be during the exam. 30 questions, 75 minutes. Okay? I've changed my mind to 75 minutes. It's 7 minutes plus 5, making 75, because I know you're going to be online. And of course, those who send letter to me, the DLC of student, they're actually going to spend 2 hours. You're going to spend an extended time. Make sure you don't spend more than your time. So all the information will actually be, you're going to receive a notification for that. I'm not going to be online with you during the exam, but it's going to be recorded. When you log on to the Zoom during the exam, make sure you are muted so that you don't disturb others. But more information, detailed information about this exam, please, I will need you to attend my revision on Monday and Wednesday. Very important, because there may not be opportunity for makeup for exam 2. Okay, I want to go into today's topic, and we're starting a new chapter. So, like I said, focus chapter 4 to chapter 6. So, which means 7. And the one we want to start today is not going to be part of exam 2. I want to welcome you once again to another statistical topic that we call one sample estimation problem. And of course, in the outline, I'm going to walk you through what is the relationship between central limit theorem and sampling distributions, then estimating single mean, then confidence interval of mean with known population variance, confidence interval of mean with unknown population variance, sample size determination, then prediction interval. Let's get started. Now, we want to start with the setup limit theorem and sampling distribution. What is the connection between them? Now, the other time, I walk you through sampling distribution. With sampling distribution, you were able to see what possible values statistic can be with a corresponding probability. Of course, even though we know, if we want to investigate, if we want to figure out the true value of a parameter, we only going to go into population once and choose the sample size. But why do we actually repeatedly go into population and choose the same sample size? We actually did that for us to be able to know what is a minimal sample size required for the distribution of the statistic to be normal. When I say statistic, okay, when I say statistic, not statistics, okay, when I say statistic, okay, it may be sample mean, maybe sample mean or sample proportion, okay, or sample proportion, okay, or difference of means, we should go x bar 1 minus x bar 2. Here, this is x bar. Here, this is p cap, or difference of proportions, or difference of proportions. P cap 1 minus P cap 2. Now, when I say statistic, it is something that we compute from sample. That is why you say sample, 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 sample. But you know, initially, this is not what we need. What we actually need is parameter. Okay? Parameter, we actually need a population mean. We need population proportion. We need a difference of population means. We need difference of population proportion. You can see the different in notations, okay? But with the idea of sampling distribution, okay, with the idea of sampling distribution, we were able to know what is a minimum sample size needed before the distribution of this, okay, will follow normal. It is only when distribution, probability distribution, because why do I say probability distribution of this? Because this is a random variable. Don't forget, if 1,000 researchers should go into a population, they work on the same thing, they choose the same sample size, they're actually going to have different values. Because they got different values, then we can look at the probability distribution of their values. How? By constructing histogram. Okay, now when the distribution follows normal, then this guy is going to be a good estimate of that guy. This guy is going to be a good estimate of that guy. This guy is going to be a good estimate of that guy. This guy is going to be a good estimate of that guy. And through sampling distribution, okay, we now realize by central limit theorem, we realize that when the sample size is at least story, when the sample size is at least story, okay, when the sample size is at least story, according to central limit theorem, the probability distribution of this will be normal. Because, you know, the requirement is the distribution of the statistic should be normal. Okay? I'm going to say that again. If I want to rely on sample mean, sample proportion, this and that, then the requirement is the probability distribution of them has to be normal. And how can we attain normality? Even though before we compute this, we take a sample from a population, even if the original probability distribution of the population is not normal, but provided we choose a sufficiently large sample, the probability distribution of the statistic will be normal. I'm going to say that again. If I want to compute this, I need to take a sample, right, from a population according to central limit theorem, even though, okay, or regardless of the distribution of the population, whether it is normal or not, we're not interested. But if we choose a sufficiently large sample, then the distribution of the statistic will be normal. And if the distribution of statistic is normal, then we're going to be celebrating, and we're going to say the knowledge of the sample can be used to talk about the overall behavior in the population. We live in a world where we only want to investigate just a subset of a population, but if everything goes the way it should go, then we can actually generalize on the result, on the sample, on the population. Does that make sense? But the only condition to do that generalization, the only condition under which that generalization is going to make sense, because it is not all generalization that makes sense. And that is why the central limit theorem puts the sample size to be at least 30. Any question? Any question? Okay, if the sample size is at least 30, then the next thing we want to do now, we want to estimate mean. Let's come into a practical situation now. Maybe I really want to know, on average, how much, on average, a college student in the United States spend in a week. Okay, I mentioned how much on average a college student in the United States spend a week. Now, what do I want to know about? I want to know this guy. I want to know this guy. But I do not have resources or resources or time. And don't also forget we're limited by budget. I'm not going to investigate all college students in the United States. What am I going to do? Then I need to take a sample of college students. When I take a sample of college students, I'm actually going to ask them, those who fall in my sample. But let me tell you this, when I want to take a sample of college students, then I need to use what I call the principle of randomization. I got to choose that in a way every college student in the United States has equal chance of being selected. There shouldn't be favoritism. There shouldn't be biasedness in the selection of the sample. Otherwise, what is going to happen? Then you're actually going to have a bias problem. Okay, when I choose a sample now, and according to central limit theorem, if I want to choose a reasonable sample, the minimum I should choose is 30. Even though when I take into consideration the population of interest, which is a college student in the United States, in terms of how much they spend in a week, even though that does not follow normal distribution. I'm talking about the population of college students in general, in terms of, how they spend per week, even if it is not normal. If the probability distribution is not normal, but according to central limit theorem, provided I choose a minimum of 30 sample size, then I can guarantee the probability distribution of the statistic, that is, of the sample mean that I obtain, will follow normal distribution. And if it follows normal distribution, then the sample mean that I got can be used to represent what I wanted in the first place. What did I want in the first place? I really want to know the average amount spent by college student in the United States. Which means if I select at least, let's say I select 50 now, whatever information I got about that sample of 50, then I will make an inference, I will make a generalization as if I've studied all the college students in the United States. Does that make sense? Is there anyone who want to ask question? Okay, now, go ahead.
Wouldn't you be careful in that situation that you're not drawing, because I'd assume you're going without replacement, right? Because you wouldn't want to ask the same student twice. So don't you have to be careful that you're not asking too many students? Isn't there some condition where it's like 10%?
Okay.
You can't generalize again?
Okay, that's a very good question. Whenever we are on the feed of a core, like whenever we're taking sample, we normally sample without replacement to save costs. And just like what you said, for us not to interrogate the same person twice. So we normally apply sampling without replacement. Does that make sense? That's a good question. Okay, now, let's say I've gotten my sample mean. Well, let me tell you this. Getting the sample mean, maybe at the end of the day when I find the mean, maybe I got, I'm talking about how much college students in the United States spend on average in a week. And maybe I collected a sample of 50, which is good enough. According to central limit theorem, maybe this is what I got. Maybe I got $200. This $200, I need you to listen now, okay? The process of getting $200 is called estimation. The process, okay, of figuring out the true value of a parameter based on sample information is called estimation, because we're estimating. We're not using everybody. That's an estimation. Now, the formula that we use, what formula are we going to use? Summation x over n, right? The formula that we use is called estimator. Take a look at that. The formula that we use is called estimator, which means estimator is a method or formula used in estimation. Does that make sense? Then the value that we got, the value, $200 now, is an estimate. You see the difference? I just differentiated between estimation, estimator, and estimate. They are not the same. Estimation is a process of you trying to figure out the value of a parameter, okay, using sample information. Then the formula that you use is estimator. The result, the value that you got is an estimate. Does that make sense? Okay. Now, because you get a single value, 200, this is a single value, then we call this point estimate. Point estimate. Point estimate. Okay, point estimate. Okay, you got a single value, point. We call it point estimate. There are two types of estimate. We got a point estimate. We got an interval estimate. Okay, we are, we also have what we call interval estimate. Okay, now let me tell you this. A point estimate could be wrong or right, even if you have done what you are supposed to do. That's a shock, right? Because we live in a probabilistic world where the approach that we're using is not, is subject to error. Go ahead.
So the 200, the estimated equation, that was like not good.
No, whenever we want to get something from sample, we always have a method to use. This is a method.
So that gave you the
That's an estimator. See, the formula you are using on sample, okay, it's called estimator. Look at an estimator, something that estimates. That's a formula, that's a method. The value that you got, what came out of the formula? Something is going to come out of the formula, right? That's an estimate. But you know what we do in theoretical statistics? What we do in theoretical statistics, we spend a lot of time on estimator. You know why? Because if the formula is wrong, then the value will be wrong. Does that make sense? Okay, now, according to the classical approach of probability, a single value could be wrong or right. Imagine you committed a loss to the research, okay, and you compute this, okay, only for this to be wrong at the end of the day. Therefore, in order to be at the safer side in research, we needed to incorporate a margin of error where we can now describe our results in an interval. That will be safe. And that is what is going to lead us to what we call interval estimation. When, in most of the research articles where they use statistical technique, you are not going to see them reporting just estimate. They will report interval estimate. Because a point estimate, which is a single value, could be wrong or right. It's 50-50. And that is the reason why we needed to incorporate margin of error. If you listen to news, whether on CNN or Fox News or ABC or whatever, when they make a prediction, after conducting an opinion poll, they will have to give you the margin of error. They're going to say within the margin of error. Okay, now take a look at this guy. Because of that, I'm coming into interval estimate now. Now, take a look at this guy. Okay, now the true value of the mean that we're looking for is this guy. The sample mean that we compute is this guy. Now you can see that, look at this entity here. If you take a look at this entity here, it's the same as this entity here. If I'm focusing, remember the other time, please, I need you to focus. All this is very, very simple, okay, if you can follow what I'm doing. Now, if I'm talking about random variable x, follow normal, okay, with this. This is to say, any amount spent in a week by college students, okay, let that amount be x. If you follow normal distribution, that will be average. For the amount, there will be variance. Now, if I calculate the sample mean and I perform sampling distribution, and if I take a sufficiently large sample, the distribution of this is also going to be normal, but the variance is going to be this. This is going to be the variance. If that is the, so what I mean is variance of sample mean is this, then the standard deviation of that now will be the square root of this guy, which is this. Now, if I have a point estimator, okay, and I want to consider incorporating margin of error, what I'm going to do, my margin of error, let's say minus E plus E, where E is the margin of error. My margin of error now will be the number of standard deviation away from this guy. How am I going to know the number of standard deviation away from that guy? It's going to be z-score multiplied by the standard error, multiplied by this guy. And that was how here, you can see z multiplied by that. So everything here is what we call the margin of error. Now what you do now, you subtract the margin of error from the mean, you added the margin of error to the mean, then which means this guy here is the lower bound. The lower value that can be the amount spent by college student can be, and this is going to be the highest value it can be. Therefore, the true value, the true average value is the mu lies in the interval. It is more reasonable. I'm going to say that again. It is more reasonable to present your result in an interval than presenting a single result. A single result could be wrong or right. The probability that a single result could be wrong or right is the same. It's too dicey. And that is the reason why we prefer interval estimation to point estimation, because in interval estimation, we've incorporated margin of error. We incorporate margin of error. There's always going to be margin of error. What is the meaning of the margin of error? The margin of error will enable us to know how, the sample reflects the overall view of the population. Don't forget, you're only focusing on the sample. You are not focusing on the overall population. Does that make sense? So, in other words, the margin of error will tell us how reliable is the estimate. If you want to know how reliable is the estimate, the margin of error is going to tell us. If the interval is very, very narrow, then that is a small margin of error. But if the interval is very wide, then it means the margin of error is huge. And you're going to hear that when they are predicting in election results, they are normally going to tell you within the margin of so value. The more the margin of error, then the less is the degree of reliability of that very estimate. Go ahead. That is a z-score that we've done the other time. That's a z-score. But the z, you can see z alpha over 2, right? It means check from statistical table under given level of significance. Alpha is the level of significance. The level of significance means the level of statistical error. We always give 5%. What is the meaning? 5% means our model cannot be trusted. Our method cannot be trusted 100%. No method, no technique in the world can be can be trusted 100%. So when I say 5%, then it means we got a tendency of misleading people 5 times out of 100. Now, if you can mislead people 5 times out of 100, then how many level of confidence do you have? 95% confidence. If your level of error is 5%. Because the level of error and the level of confidence, they are mutually exclusive. Does that make sense? Okay. Now, like I said, the lower and the upper. And let me tell you this. Whenever you are working on confidence interval, we normally associate that with the level of confidence. Mathematician will tell you whenever you present a result in an interval, there will be error. Does that make sense? Whenever you present results in interval, there will be error. Now, if I want to present something in interval, I need to tell the world the level of my confidence. So if you want to construct a confidence interval, I could say, okay, construct 95% confidence interval. Construct 90% confidence interval. What do I mean by 95% confidence interval? Oh, that means if I construct 100 intervals, please listen. If I construct, how many intervals? 100. If I say 95% confidence, if I'm using 95% confidence, it is only 95 intervals out of 100 that the true value will lies. That means it is not, the true value that we're looking for does not lie in all the 100% of the interval. If the true value lies in all the 100% of the interval, what are we telling the world? We are telling the world our method is perfect. No method is perfect. I told you from day one, we want to depict reality using model, but the facts remain, model is not the same as reality. The model will give us an approximate reality. There's always going to be an error. You know why I like statistics? I like statistics as a course because statistics appreciate the fact that you don't need to be surprised by anything in this world because there's always going to be surprises. Okay? Because if your model is perfect, we shouldn't have surprises. Why surprises? Why surprises? Surprises come because of the fact that the model is not perfect, because there's always going to be formation loss, which is the error. That's what we're trying to minimize. Take a look at this. Here, the true value is at the center. How many? And I constructed 10 intervals, like 100% of the interval. Which one does not contain the true value? The one of number 4. Do you see this guy? You can see that it does not pass through this guy. This is an example of a 90% confidence interval. 90% confidence interval means out of 100 intervals, it is only 90 intervals that will contain the true value of the parameter we're looking for. Does that make sense? Okay. Let's go to an example now. Okay. The average year concentration recovered from a sample of measurements taken in 36 different locations in a river is found to be 2.6 grams per millimeter. Find the 95% and 99% confidence interval for the mean zinc concentration in the river, assuming that the population standard deviation is 0.3. Now, I need you to listen now. If I ask you to construct a confidence interval about me, it can be done in 2 ways. You need to ask yourself a question. Am I going to use a confidence interval that has a Z score, Or am I going to use a confidence interval that has a t-score? There's a z-score, there's a t-score. What determines whether we should use z or t is when the population variance or the population standard deviation is given. If the population variance is given or population standard deviation is given, we're actually going to use the formula that involves z-score. But if the population variance is unknown, it's not given, and you're actually going to use a sample variance or sample standard deviation, you're actually going to use the formula that has a t-score. Now, when you take a look at this now, please, I'm going to circle that here so that you're going to see. Take a look at this. What did they say? Assuming, please pay attention to stuff like that. I'm seeing some final exam questions here now. Assuming that the population standard deviation is 0.3, here you are giving population standard deviation, then you're actually going to use the confidence interval, the formula of the confidence interval that that contains z-score. Now, and let me also tell you this. We're going to be making use of a table, normal table, okay? And here they say compute 95 and 99. If you want to talk about the range of a confidence interval for the same question, 99% will be wider than 95. Does that make sense? Now, let's say, for instance, you write exam, and I say, okay, professor, can you tell me what is my score? And I say, okay, you know what? I'm 100% confident your result is between 0 and 100. Does that make sense? That is normal. Your result is between 0 and 100. That is a very wide range. Does that make sense? So the higher level of confidence interval, okay, will be characterized by a wider range. Does that make sense? Please take note. Now, how do I compute this? They've given you the mean. What formula are we using? We're actually using this formula. We're using this formula here. You already have your mean, sample mean given. They give you samples. This is a population standard deviation. This is the sample size. This is the one we're going to check from the table. Now, if I want to check from the table, I need alpha. Oh, how am I going to get my alpha now? What do we call alpha? Alpha is the level of statistical error that we call level of significance. How am I going to get my alpha? Then I'm going to look at what do they give you? The level of confidence. If the level of confidence is 95%, then your alpha is 5%. Does that make sense? Because level of confidence is 1 minus alpha. Alpha is 1 minus level of confidence. Does that make sense? So if I'm going to check from a statistical table, okay, since they mentioned 95%, my alpha will be 0.05. It's going to be 5%. Then I'm going to do 0.05 divided by 2. Don't forget, in the formula, what do you see? Alpha divided by 2. So when I do 0.05 divided by 2, that will be 0.025, right? And when you have a 0.025, then you will do 1 minus. You subtract that from 1. When you subtract that from 1, that will give you this guy. Do you see how I got the 0.975? It's 0.975 is what I'm going to check in the table. I'm going to check in the normal table. Okay, what values of z give us is 0.975. Okay, so checking from the table now, the values of z that will give you 0.975 is actually going to be 1.96. Which table am I talking about? Table A.3 in the textbook. Here we want to figure out what was the values of Z if the probability is 0.975? And that would be 1.96. Now that's what you're going to plug in. 1.96. This is the standard deviation given, the sample size. Whatever you're going to have here is also what you're going to have here. The only difference is you are adding to that, you're subtracting, then you're actually going to get two values, the lower bound and the upper bound. Okay. This is for the 90%. I want you to see, what is it? This is for the 99. Take a look at this. For 95%, the Z-score was 1.96. For 99%, the Z-score was 2.575. Now, let me tell you this. When the level of confidence increases, the Z-score you're going to check from the table also goes up. Go ahead.
You said this is going to be like a question. Like the Z-score from like the table. Like, will the table be given on the exam?
Of course. Of course. Can I tell you this? Even me, I can't do it without looking at the table. They said the table will be provided. Okay, even in the exam too, you may want to make use of some table. Of course, I'm going to tell you, I have access to that. Yeah, go ahead. Oh, okay. I'll just 1.96 change to 2.575, right? Now, this is what happened. Let me first explain how I got 1.96. Now, at 95%, I need to first figure out my level of confidence and my level of significance. So, which is going to be 1 minus 0.95, which is 0.05. Then I divide 0.05 by 2. That will be 0.025. Then I subtract that from 1. That will be 0.975. Then I will go into normal table. I'll check the body. The 0.975 is a probability, right? Then what was the values of Z-score that give us that? That was 1.96. Now, if I want to do the one for 99, what would be my alpha? For 99, so that would be 1 minus 0.99, right? Alpha will be 0.01, okay? If the alpha is 0.01, I divide that by 2. I subtract from 1. When I subtract from 1, I will go to the table again and check what values of Z that will give us that. So definitely, if alpha changes, then it is expected that the Z-score also changes. So the Z-score here that gave it 2.575, that is that's a Z-score for 99% confidence. I remember when I was in school, there are three common Z-score that we cram that are very common in literature. Okay, level of confidence. Okay, level of significance. Okay, then Z alpha over 2. Take a look at that. Okay, if this is 90, these are the common one. Okay, 90, this is going to be 10%, which is 0.1. Okay, and if this is 95, this is more or less going to be 1.645 in the table. Okay, this is 5%, is 0.05. This is 1.96. For 99%, okay, this is going to be 1%, 0.01, 2.575. These are the common one. Okay? What do you notice? When the level of confidence is increasing, what happened to the Z-score? The Z-score is going up. Take a look at that. Now, that is it. And at the end of the day, this is what we got. You see what we got? Now, what would be the interpretation? So we're going to say we are 99% confident that the true value of the average is between this and this. Whenever you are interpreting, you have to tell us the level of confidence. Don't forget, we actually got this value here. Okay, we got the value there, putting into consideration the level of confidence. Okay, now, and that guy I told you, this guy here, is what we call the margin of error. That was what we subtracted and what we added. Okay, now, is there any question? Go ahead.
So you said you're 99% sure the values between that because that was a higher degree of confidence.
No. Well, I said we are like, if I want to interpret this now, you need to tell us that level of confidence used. So you're going to say we are like we use 99 here. We are 99% confident that the true value of the mean lies between that and that.
But in the question we had 95% and 99%.
Yeah, this is the one for 99. You're also going to interpret the one, like when you solve this one, you will get the one for 95.
Oh, okay.
But you know what you're going to notice? If you get your interval here and you compare with the interval here, the interval here will be wider. Does that make sense?
Yeah.
Okay, so that is what that actually implies. Now, you know what I want to do? I'm going to take, let me use the next 5 minutes to just say this. I'll take this topic again. Like, I'm going to start from where I want to stop now in the next lecture. But let me tell you my plan. Next week, Monday, Wednesday, we're going to be here for revision. Friday is going to be exam. And the other week, that week is a Thanksgiving week. I've already uploaded 2 lectures for Thanksgiving week, but that Thanksgiving week we're not having lecture on Friday, the Thanksgiving week. But we're going to have in-person lecture on Monday, but we're going to have lecture through the Zoom on Wednesday. The Wednesday, the penultimate day to the Thanksgiving. Thanksgiving is on Thursday, right? I'm going to say this again because I want us to plan. Okay, in the Thanksgiving week, we're going to have an in-person lecture Monday. Okay, and on Wednesday, okay, then we're not going to have lecture here. It's going to be through the Zoom. Okay, you can be, because I know some of you may want to travel. Then you're always just need to log on to the Zoom wherever you be in the world. But make sure you stay safe, okay? Make sure you all stay safe, okay? Now, there's not going to be any lecture on Friday, Thanksgiving week. Then we're going to meet again. But you know what? I want to beg you, if you have friends that are not in class right now, you can say the class now. I want to believe that maybe some of them are having midterm too, other courses. That's no problem. But tell them to be around on Mondays and Wednesdays next week, because I'm actually going to walk you through some questions. And watch out today for exam 2 guide. I'm going to put this on the note of the announcement section. Okay, bye for now, everyone.